This is AP Calculus 7, 4, 5, 6, and 7. I'm doing all of these in the same section because they go so well together. One just leads right into the other. These are very important sections as far as preparing for the AP test. There are always several questions on these particular types of problems. So I want to make sure that we cover the basics here, and then we will do a lot of practice with this in and out of class. For section 7.4, that title is Reasoning Using Slope Fields. And basically what we are learning here is, what does a slope field represent? Remember, we learned that y prime is the same thing as dy over dx, and what this means is y prime is equal to dy over dx. The slope of the tangent line, this is also the slope of the tangent line, can be found by plugging in to the differential equation for any x, y point. So if they tell you that dy over dx equals 0, that means there is a horizontal tangent line or a horizontal slope at that particular ordered pair x, y. If dy over dx, the slope is undefined, then that means there's a vertical slope at a particular ordered pair x, y. If dy over dx is greater than 0, that means that the slope goes in a positive direction. In other words, it's looking like this. And if dy over dx is less than 0, then it has a negative slope at a particular ordered pair x, y. So it would be in this direction. A typical example in this section would be something like this. They'll give you a differential equation, dy over dx equals x over y. So the derivative of the function with respect to x will equal x over y. And then they'll ask you to find the slope of the tangent line at a particular point, or at certain points that they give you. And so here they gave us 4 points. So to find the slope of the tangent line for this differential equation at the slope, or at the point 1, 2, we're going to plug the ordered pair 1, 2 in for x and y. So what this means is, if we were to do that, dy over dx equals 1 over 2. For b, if we plug 2, 0 in, if you think about that, we would have 2 over 0, which is an undefined slope. So at that point, the slope of the tangent line would be vertical. At the point 0, 4, if we plug that in for x and y, we'd have 0 over 4, so that slope would be 0. That would be a horizontal slope, so that's where we would have either a maximum or minimum, depending on whether it's concave up or concave down. And then the last one, if we plug negative 6, 3 in, we would have negative 6 over 3, which gives us a negative 2. So we know that the slope of the tangent line there would be in a negative direction. Another thing they will do is they'll give us a slope field, and they will give us a differential equation that represents that slope field, and they will want us to describe all points on the xy plane where y is not equal to 0, for which dy over dx is equal to negative 1. Now let's talk about why y can't equal 0. If you think about that, if y were equal to 0, wouldn't that cause this to be undefined? So we can't have y be 0 if we want this condition. So dy over dx is equal to negative 1. Well, we know that dy over dx equals x over y. So to figure out all the points where we would have the slope of the tangent line equaling negative 1, or the conditions that would cause this to happen, couldn't we just replace dy over dx with what it equals, negative 1, and then solve the equation for y? So that's what I'm going to do. We know that dy over dx is equal to negative 1, so what we have here is x over y equals negative 1. And if we just solve this for y, if we multiply the y on the other side, and then we divide by the negative to get y by itself, we will have the condition that causes us to have a slope at negative 1. And what this is saying is the slope of the tangent line will be negative 1, or our differential equation equals negative 1, when y is the opposite of x, or x is the opposite of y. Now let's think about that. Think about ordered pairs where we have opposites. Like, let's think about 0, 0. Well, 0 and 0, there it's its own opposite, right? It can't be positive or negative, but they did say that y cannot equal to 0. So this would not be a situation that we're talking about. If that's a common point we tend to pick, but sometimes we can't pick it just because of y equals, or y can't be equal to 0. So I wanted to make sure I pointed that out. They've already specified we can't use y is equal to 0. So in this case, that's not a point we want to use. So here I've listed a few points where x and y are opposites. 1, -1, -2, 2, 3, -3. And let's just look at the slope field here at those ordered pairs. At 1, -1, it looks to me like that is an ordered pair, or that is a slope of -1. At -2, 2, right here, that looks like a slope of -1. At 3, -3, looks like a slope of -1. And if you just look across this entire slope field, doesn't it look like all of these opposite points would have the same slope of -1? And that's what this is demonstrating here, that the slope field, when your x and y are opposites, the slope field will have a slope of -1 in all of those points. For this one, it says find the slope of the tangent line for the given differential equation at the given point. Okay, so they've given us a differential equation, dy over dx equals 2 times x minus 1. They're asking us to find the slope of the tangent line. Well, and they gave us the point 3, 2. So they're asking us to plug 3, 2 in to this differential equation. So if we do that, we'll have dy over dx equals 2 times 3 minus 1. And 3 minus 1 is 2, so 2 times 2 is 4. So the slope of my tangent line at the ordered pair 3, 2 is 4. And if you look at this line here, we can tell that that's going to be a very steep slope here. So it very likely would be 4. So we can see that the slope of the tangent line at that particular ordered pair would be very steep. And we know, based on the differential equation, that that slope is 4. Now they're using the same graph, the same differential equation, and we're going to find the general solution using separation of variables. Now, if you think back to the beginning, you may wonder why we skipped 7.5. That's because that's a BC topic only. We're doing AP Calculus AB this year, not BC. BC covers quite a bit more. So 7.5 was just for BC, so we don't have to cover that. That's why I'm skipping to 7.6. So the next thing they're asking us to do is find a general solution given a differential equation. It says integrate the differential equation to the right to find the general solution. So basically what they're asking us to do is go backwards and find the f of x function, or the y equals function here. So they want us to integrate this. Now, when we integrate both sides of that, what we're going to have looks like this. So to set this one up, I went ahead and distributed the 2x minus 1. You don't necessarily have to do that. In my case, I just think it's easier to, so that's why I did it. But again, it's not necessary. You can get the same answer without doing that. And when I set this up, if they've asked us to integrate this, before we're allowed to integrate, we have to separate the variables. In other words, all the y's need to go with the y's, and all the x's need to go with the x's. So notice here, this has got a dx on the bottom, and this has an x over here. So I need all these x's to be with these x's. So I'm going to move the dx over. And this is what we call separation of variables. So I'll have left a dy equals 2x minus 2 dx. So I moved the dx, remember that represents the derivative of x, to be with the x. There were no other y's in this differential equation. I wanted the first one to be fairly simple. So I didn't have any y's to move over here. A lot of times though, you will have a y, and we'll get to that soon. So now what they've asked us to do is integrate this. So if they want us to integrate this, what we're going to do is put the integration symbol in front of each side. And when I do this, it's a simple integration. Now, the integration of dy is just y. And since they've asked us to find the general solution, we are finding the f of x, or the y equals function here. Then if I integrate this side, I would get the general solution, x squared minus 2x plus c. I need the c here because this was not a definite integral, it was indefinite. So this is the general solution that I get once I do separation of variables and integrate. This takes us to lesson 7.7, finding the particular solution using separation of variables. If you're asked to find the particular solution, you have to find the general solution first, then plug the ordered pair into what you got to get the particular solution. So you see how these two go hand in hand. They're very similar. So what I'm going to do is I'm going to copy that equation that I got in the last screen, put it here because that was our general solution, and then show you how to take that from a general solution to a particular solution. So we've already integrated the differential equation and found the general solution. So back at my other screen, that general solution was y equals x squared minus 2x plus c. So I've copied the general solution here. To get the particular solution at the given ordered pair, I'm going to plug in that ordered pair 3, 2. I'm plugging in the 3 for x and the 2 for y. So when I plug the ordered pair 3, 2 in, this is what my plug-in looks like, and my next step is to solve for c. So when I solve that, I get c equals -1, and then my particular solution is the equation I get when I replace c with what it equals. So the particular solution at the ordered pair 3, 2 is y equals x squared minus 2x minus 1. And that's the particular solution at the point 3, 2. Keep in mind, I could give you any ordered pair on this coordinate system to find the particular solution, and your c value that you get when you plug in other ordered pairs will most of the time be different. So you can have an infinite number of particular solutions depending on the ordered pairs that I give you. But each one of these is only going to have one answer because we're only talking about the particular solution at a specific point. Now, to go a little bit further with this, if they ask us to find the equation of the tangent line for the given differential equation at the point 3, 2, well, they want to know what the equation of the tangent line is that goes through this ordered pair. So if you think about that, in order to get the equation of this tangent line, we need two things. We need the slope and we need an ordered pair. Well, we already have the ordered pair, 3, 2. They gave us that. The slope is what we get when we plug 3, 2 into this equation. And I believe, didn't we find that already? Wasn't dy over dx at that particular point 4? So if that's the slope at the point 3, 2, and we have the point 3, 2 and the slope that we need, all we need to do now is put that in point slope form. So the equation of the tangent line at 3, 2 is y minus 2 equals 4 times x minus 3. So here is another one. It says find the general solution to the given differential equation dy over dx equals x plus 2. Go ahead and pause the video, see if you can get that general solution. Remember your general solution will have a plus c, but see if you can separate the variables, integrate that, and get your function with a plus c. Go ahead and pause the video. So here is the general solution I get for this one. First, I separated the variables. I moved the dx over to be with the x. And then I took the integration of both sides. The integral of dy is y. The integral of x plus 2 is 1/2 x squared plus 2x plus c. You could have expressed this as x squared over 2. Either way is fine. So we also need to understand how to deal with these when we have a y within these equations. So this says the same thing. Find the general solution to the given differential equation. Dy over dx equals y plus 2 this time. So we're finding the differential equation of y with respect to x, but there aren't any x's in here. But if we integrate it correctly, we'll have some x's as we finish. So let's look at this one. First thing I'm going to do is, again, I'm going to separate the variables. Now, if you think about what that means, I'm going to take this dx and move it to the other side because I need the y's with the y's and the x's with the x's. So I'm going to move the dx to the other side. So I've got dy equals y plus 2 times dx. Now, there's a problem here. I have the y paired with the dx. That y needs to be with the dy in order to integrate. So I'm going to divide both sides by y plus 2 and get that y with the dy on the other side. So when I do that, this is what I get. So I have dy over y plus 2 equals dx. Now, you might be tempted to try to do dy minus y equals 2 dx, but you can't do that because if they're attached with addition or subtraction, they go together. They have to be moved together, and you'll see why when we integrate. At this point, I'm going to put the integration symbol in front of both of these, and now I'm going to integrate. Well, if you look at the side, that is a natural log situation. The derivative of y plus 2 is dy. So that would be the natural log of the absolute value of y plus 2. And when I integrate this side, the integral of dx is just x. So we need an x plus c. And now, if we're getting the general solution, don't I need to get y by itself? So if you think about that, in order to get y by itself, I'm going to have to get rid of this natural log. So think back to your Algebra 2. How do you get rid of a natural log? Hopefully you're saying we'll put an e in front. So I'm going to put an e in front of both of these. I've got e to the natural log of the absolute value of y plus 2 equals e to the x plus c. Dealing with this can be tricky. So let's see what happens. Well, over here, e to the natural log of y plus 2 is going to be y plus 2. Now let's think about that. We can drop the absolute value at this point because if it's attached to a natural log, wouldn't this have to be a positive? It's not going to be negative because the natural log of a negative is undefined. It can't be negative. So I'm going to drop the absolute value here because we know it can't be negative because of basic rules of natural logs and logs. And then over here, this is the tricky part. If you think about this, e is to the exponent of x plus c. So we've got to think about what that means in terms of monomials. And let's think back to Algebra 1. If you had something like x to the 5 plus 3, wasn't that the same thing as this? X to the 5th times x to the 3rd. We know that when the bases are the same, we keep the base and add the exponents, giving us this. Well, isn't that the same situation we have right here? Doesn't this represent e to the x times e to the c? So if you think about it this way, now let's think back to what c means. C is a constant. So we don't know what that constant is, right? Well, don't we also know that e is a constant? E is a number, right? So if we have a constant to a constant, so a constant to the power of a constant, isn't that still just a constant? So instead of calling this e to the c, we are going to call it our new c value. So we're replacing e to the c with our new c value. So we have c times e to the x. So what this means is y plus 2 equals c times e to the x. And then to get y by itself, we would subtract the 2 over. And this gives us our general solution for this differential equation, okay? So the c is still our constant. Now, if they ask us to do a particular solution for this, and they gave us an ordered pair, it would be very simple to find c by plugging the ordered pair in for x and y. And we'll do that soon. Here it says find the general solution for the given differential equation. Y prime is equal to 5x over y. Now let's think about what y prime is. Isn't y prime the same thing as dy over dx? So you have to understand that y prime is dy over dx because in order to find the general solution, we have to separate the variables here. We have to get the y's together and the x's together by moving these to opposite sides and doing the separation of variables. So to separate the variables here, I'm going to move this y over here with the dy, and I'm going to move the dx over with the 5x. So that gives me y dy equals 5x dx. I would integrate both sides, and when I integrate, this side gives me y squared over 2, and this side gives me 5 halves x squared. I have to remember the plus c. Now you may be asking yourself, why do we need a plus c over here but not over here? Well, if you think about it, if we don't know what c is a constant. If we put a c over here and a c over here, if we then combine those two c's, wouldn't we still just have a c? We don't know what either one of them are anyway. So as long as you put the plus c on one side, you're good. You don't have to put it on both. And so for the general solution here, I'm going to multiply by 2 on both sides. Now let's think about what we have here. 2c, well, we don't know what c is. So if we multiply c by 2, don't we still have an unknown number? So we don't need the 2c here. We just need that to be c still. So we have a y squared equals 5x squared plus c. And for this one, I would just leave it y squared equals 5x squared plus c. If you take the square root of both sides to get y by itself, then you're ending up having the square root of a c value, an unknown. It's just best for this to leave it y squared instead of trying to get y by itself. So for this one, it says find the particular solution to the given differential equation using the initial condition y prime equals x times 6 minus y, and the ordered pair is 0, 0. So the first thing I'm going to do is recognize that y prime is dy over dx. Next, I'm going to separate the variables. Then I will integrate both sides. Oh, notice here, this 6 minus y has to stay together. It has a y, so it needs to be over here with the dy. So it's dy over 6 minus y. And here we've got just the x, multiply the dx on the other side. Then I'm going to integrate both sides. When I integrate, on the right-hand side, that's pretty easy. That will be x squared over 2 plus c. On the left side, we do have a natural log situation. If this is your u, the derivative of u is negative 1 dy. So we need a negative on the inside and outside here. Negative here, and a negative on the outside to offset it, so we're not changing its value. So now we have u du. So we've got du over u, which is a natural log situation. So that would be negative the natural log of the absolute value of 6 minus y. So I know in order to get rid of the natural log, I am going to need to put an e in front, but there's a problem here with that negative. I want to go ahead and get it on the other side. So if I divide both sides by a negative, I'll have the natural log of the absolute value of 6 minus y equals negative x squared over 2 plus c. Now you might be saying, well, shouldn't that be a minus c? No, we didn't know what c was. Addition symbols are easier. So even though we're multiplying this by a negative, it doesn't matter. We don't know whether c is positive or negative anyway. So just keep it a plus c. You don't have to worry about that. It's an unknown. We'll find it later by plugging numbers in, but we won't do that yet. Now, the next thing I need to do is get rid of the log, or the natural log. So to do that, I'm going to put an e in front of both sides. So this cancels out the natural log. We know 6 minus y has to be positive, so we're going to drop the absolute values. So when I do that, remember this is e to the negative x squared over 2 times e to the c. So that e to the c is just now the constant, and it moves to the front. And then to get y by itself, I would move this over with the 6 and the y to the other side. That gives me 6 minus c e to the negative x squared over 2 equals y. Then to get the particular solution, I'm going to plug 0, 0 in for x and y. So if I plug 0 in for x, doesn't that give me a 0 here? And e to the 0 is just 1. So that means 1 times c is just c. So we have a 6 minus c will equal 0 because we've plugged 0 in for y. So that means if I move c to the other side, c will equal 6. So that gives me the particular solution, y equals 6 minus 6e to the negative x squared over 2. So in this one, it says to find the particular solution to the given differential equation using the initial condition y prime equals xy, and then the ordered pair is 0, 1/2. Go ahead and pause the video, see if you can get this one on your own, and I'll give you the answer in just a few minutes. And here's the solution for that one. dy over dx equals xy. We know that y prime is dy over dx. I separate the variables, and I have dy over y equals x dx, and I'm going to integrate. When I integrate this, it is a natural log situation, so that's the natural log of absolute value of y, equals, that would be x squared over 2, and then we have a plus c. And then, if I put an e in front of both sides, I have y, we can drop the absolute value because it has to be positive, equals e to the x squared over 2 times c, because remember this will be e to the c, which is still c. Then we plug in the ordered pair. 0 goes in for x, leaving us with e to the 0. 1/2 goes in for y, so 1/2 equals c e to the 0. E to the 0 is 1, so that means c equals 1/2, giving us the particular solution, y equals 1/2 e to the negative x squared over 2. This is a delta math example. They are wording it a little bit different. Instead of giving you the ordered pair 3, negative 2, they're writing it as a function ordered pair, which is fine. And here, this is very similar. So go ahead, pause the video, see if you can get this one, and I'll come back with the solution in a minute. So for this one, I first separated the variables. I put the 3y squared with the dy, and the 2x squared plus 5, I moved the dx over. I integrated both sides. This is a simple integration. This is y cubed equals 2/3 x cubed plus 5x plus c. Then I plugged in the ordered pair. I plugged in negative 2 for y, negative 3 for x, and when I did that, I was able to find c equals 25. Then I plugged the c value back into my antiderivative. So y cubed equals 2/3 x cubed plus 5x plus 25. And then delta math is going to want you to express that as y equals or f of x equals. So that would be the cube root of 2/3 x cubed plus 5x plus 25. They should also accept if you put 2/3 x cubed plus 5x plus 25 in parentheses and take that to the 1/3 power, that would also work. Just be very careful when you're entering things into delta math with the syntax that you're making sure you're putting parentheses around things that need them, so that delta math will understand exactly what you're talking about. And then this is a good example. They had shown this on one of the AP videos, so I copied it to show you here. If you're trying to determine which of these equations could possibly be this differential or this slope field, basically really all you have to do is determine what each of these equations might look like as a graph. So if you think about that, y equals x squared, well, that's a parabola going up because it's a positive a value. So that would be a parabola that looks something like that. And actually that would go through 0, 0 because there's no whole number value there, but that would be just a basic parabola. Y equals e to the x. If you think about the shape of an e to the x function, doesn't e to the x go through 0, 1 and go up indefinitely very quickly, something like that? So that's what the e to the x function would look like. Then if you think about what the e to the negative x function would look like, it's very similar to the one above, but it's in the opposite direction, going up toward the left indefinitely. If you think about the cosine example here, we know that cosine crosses the y-axis at 1, and our cosine function looks something like this. It has a curve that's something like this. That's close. It's not perfect. And then y equals natural log of x. I'm going to put that over here. Wouldn't that function, since that's the inverse of e to the x right here, and this goes through 0, 1, wouldn't that function go through 1, 0 and kind of be the opposite direction? It would go down this way and up this way. So if you just think about which one of these graphs can compare to that slope field, well, if I just pick a particular point here, let's just say this point right here, and try to follow where that slope field would be, wouldn't it do something like this if we follow that slope field? And which equation looks very similar to that? Well, I would say that would be E. It's the only one that matches even closely at all. The others are all going in pretty much opposite directions. So we can say E is the best example or the best equation for this slope field.